Hi all, welcome to the sixth tutorial on the course on operation systems. We are continuing our discussion on the operation system that was developed and implemented by MIT, which is xv6, that is a redundant open source code of this operation system implementation. And today we're going to study and delve deep into the code of how the boot is loading, meaning firstly while pressing the power button in your PC, and now the operation system start and the kernel is loaded and so on. So last week we talked about an introduction to the xv6 operation system, and also we had some general knowledge about how the x86 architecture is made of, which this operation system is based on. And we saw the registers, some important registers, and so on. So let's begin. I already made a video in this subject and uploaded it, but noticed that the audio was muted. So now I'm redoing this tutorial. Okay, so how the boot is processed. So generally, when you open your PC, so there is a code that we cannot get into. It is in the non-volatile memory in your motherboard, in a ROM memory, which is called BIOS. BIOS is as the name suggests, basic input-output system, meaning that is a code that is not even written by the xv6 by MIT. It is a code that we fetch from a ROM, and it starts initializing the hardware. After this initialization, the BIOS fetching a code in the first sector in the boot disk. The boot disk is just our general disk. We just call it a boot disk because the boot loading code is in this disk. So, and we save it in the first sector at address 7C00. So the BIOS job prepares the hardware and then transfer control to code loaded from the boot sector, the first 512 byte sector, which is a very small amount of code of the boot disk. This boot sector contains a code that is called bootloader. Okay, so first of all we have the BIOS. The BIOS do a simple hardware initialization and then call the bootloader from this address 7C00 that is based on from the first sector in the boot. Okay, so the BIOS load the boot sector at memory address 7C00 and then set this processor register IP instruction pointer to this address. A small hint and a small thing I want to say is that this register is called IP, instruction pointer. And last week we talked about some important control registers and useful registers. One of them was EIP, and we said that the E in the beginning of the naming suggests that it is a 32-bit register, but here we don't have this E in the IP. So this suggests that the computer is initialized in a 16-bit memory, in 16-bit architecture, and part of the boot process will have to switch from this 16-bit implementation into a 32-bit implementation. Okay, so when the bootloader begins executing, the processor is simulating an Intel 8088. An Intel 8088 is a very old, like in the 70s, CPU, which means that we are still simulating when initializing the BIOS and the boot process. It is in 16 bits. So the bootloader job is to put the processor in more modern operating mode, meaning switching from 16 bits to 32 bits. Load the kernel xv6, the xv6 kernel from disk into memory, let's see it, and transfer code to this xv6 kernel. Okay. The xv6 bootloader is comprises of two source files. One is an assembly code called bootasm.s. It is an implementation. It's a code that we're going to see. It was made by MIT, xv6 code. So it is in line 900, 100 in the book, the listing, meaning the listing is this listing, okay, 900, 100, 100 is this. You can see all the code. We will go through everything. And there is a code. This code calls this code, the other part in the bootloader. It is called bootmain.c. That is written in C. And you can see it, by the way, that there is a switch from an assembly code to a C code, and we'll see how it is made in the code, the switching from stack to code. And just a clue about it is we need to initialize the stack pointer and the heap and all the structure that is important for processes in C to run. So we'll see it in a moment. Okay, before going further to the implementation of the boot process, we need to make some initial understanding about how the memory is working, the memory mapping especially, and we're going to see much more information about this in 2 weeks from now. So I'm just going to go through it very, very fast. So generally, the code is implemented with a virtual address, meaning that each process should think that it has all the memory and all the, if you have 4 GB RAM, then it will have all this memory to run on. And also we don't want that two processes run concurrently. We don't want that each process will access the same memory. So for these issues, we have a mapping from virtual address to physical address, meaning that each process will have a section in the physical address which it will run on. And there are two stages for this translation from virtual to physical. The first is the segmentation mechanism that switch from virtual address into linear address, which is somewhere in between. And the linear address will switch into physical address by paging. Okay, and the reason that we have two staging in this translation is for two reasons. The segmentation is mainly working on protection, meaning that a process, if it is a kernel process, or if it is a user process, we want protection, that we don't want to access. We want kernel to be able to access any place in the physical address, but user processes will not be able to get into segments that are kernel. So this is mainly for protection. And the paging is mainly for what we just told, that we want each process to think that it's run on the entire physical address, but the real case in the physical address is that each process has a local space in the physical address that we point to. Okay, we're going to have much more conversation about it in 2 weeks from now. This is a more detailed information of how this mapping is working. I'm just going to go through it really quick, and we'll talk about it in 2 weeks from now. So you have a segment that memory is divided into. So the logical address will contain the first segment selector. We select the segment, and an offset within the segment. Okay, so the segment selector select the segment, and with the offset we can get into a linear address, and from this linear address we have in the linear address you have directory, page, and offset, which means that we go into a directory table with CR3. CR3 point into the main directory table, and the directory is an offset within this directory table. And with the page, we're going to get into a specific page table with this offset of the page. And then with another place in the linear address, we have the offset to get inside the physical address. Okay, two important things to understand from this talk for later conversation on the boot is this GDTR, which is a global description table register, which point into this main first table, that point into the kernel executable. We do see it. We need to initialize this GDTR, and we need to initialize this CR3, which is a control register that point into this important directory table. Okay, so we saw it before. Right now, CR3 is a control register, part of the control registers, CR0, CR1, CR2, CR3, which point into the directory table. CR2 is responsible for if you have any page fault that we cannot access any of the page table. So we have a page fault, and this is important for this task. We'll talk about it in 2 weeks from now. CR1 is reserved. We don't have anything here, and CR0 has two main bits, PE and PG. And PE is, it's more detailed here. PE in CR0 is a flag for protection enable. Protection enable is when we have a 16-bit mode in the CPU, then it's called real mode, and when we switch into 32-bit mode, it's called protection mode. So when we are in protection mode, when we're going to switch to protection mode, we're going to enable this CR0-bit PE to 1. When this bit is set, the protection mode is enabled. When we set the real address mode, meaning 16 bits mode, is entered. PG is a paging signature, meaning when this bit is set, the paging mechanism is enabled. When reset, the paging mechanism is disabled. Okay, so by initialization of the computer, this CR0 will be 0, meaning that we are not having protection mode, and we don't have any paging mechanism, meaning that we have one-to-one mapping from virtual address into physical address. Okay, so CR0 is reserved for future, CR2 contains linear address that causes a page fault. We will talk about it 2 weeks from now. CR3 contains a physical memory base address of the page directory. So this register is also called page directory base address. Okay, let's go in more details on the implementation of the bootloader in the boot process. So when the bootloader begins executing, the processor is simulating an Intel 8088 in real mode, as we said. It starts the execution at memory address 7C00. What it does is switches to protected mode, meaning 32-bit mode. It sets up the global descriptor of table, which is this register, which is important for the mapping from a virtual to physical address. Okay, then the bootloader set up the GTT, and then with this setup, the bootloader enter protected mode 32-bit and logical address and maps one-to-one to physical addresses. Okay, so a little bit more detail about how the code is implemented. Let's see it in the code. You can see it here, but I prefer right now to use the terminal. Let's enter. Okay, see it all the files of the boot process. Let's enter using vim the boot asm.s. Okay, you can see it here. So let's understand what we have here in general, not. So we are in a 16-bit mode. We're starting with a 16-bit mode, and then the first task is to disable interrupts. What is this interrupt? Generally, when you open your computer, you can like move the cursor and or click like F1 or F2 to switch into another USB mode or something like this. But yes, since it is a redundant operation system code, we do not allow any interrupts in order for this code to run without any interruptions. Okay, so first of all, we don't allow any interrupts. And then we're going to initialize important registers, segment registers that are responsible for the mapping from virtual address to physical address. We want to zeroing them, meaning that the segmentation mechanism will not work, meaning that if we have a virtual address, it will map into a physical address one-to-one. How we do it? AX is an auxiliary register, which we set to 0. How we do it? We XOR it by itself, which means it will be 0. And then we assign this value to all the segment register on data X time stack. Here is a workaround, not going to go through. This is just something that was implemented because the address was 21 bits and we have only 20 1 megabyte of physical address, which is 2 by 20. So this is just a simple workaround. I'm not going to go through. Not important. And then I want to switch from real to protected mode, meaning from 16-bit to a 32-bit. Then what we do is first set this bit in the CR0 to 1, meaning that we're going to switch to a protected mode. we're going to load the bootstrap GTT. This is the register that we talked about in here in the mapping of the virtual to physical address, and that's it. We completed translation to 32 bits protected mode by using a long jump to reload the CS. Okay, and EIP, which is an instruction pointer, and the segment descriptors are set up with no translation, so that mapping is still identity mapping. We are still mapping from one-to-one virtual to physical address. And then we start the code in 32 bits. Now we're going to want to jump into a boot main.c. We finished our task in this assembly code. And the way we do it is by initializing, saving the stack values, and set the stack pointer to move to start. And then we call boot main.c. We do not expect any return from this boot main, but if it returns, then you have this code. We're not going to go through it. We're just having a while loop, but we're not going to go through it. So we're calling bootmain.c. Oh, so how the code is made of? We have cleared any interrupts. We don't want any interrupt, and zero the registers DSESSS. The reason that we disable interrupts is because, first of all, we don't know how the BIOS left those two registers, so we need to initialize them to zero ourselves. Second of all, we disable interrupt in order to make sure that these registers are zero and do not change. Okay, then we have this workaround which we didn't go through, which is not important in the code. Then we switch from 16-bit to protected mode, which is 32 bits. We switch into this 32-bit, jump to this loading of 32-bit mode, and set up protected mode data segment register, set up the stack, and then when we set up the stack, we call boot main .c, and we should not return. If we return, there's some infinite loop, and I'm not going to go through this. Then we are at bootmain.c. So generally, bootmain.c is responsible after we had initialized to 32 bits and did some initial initialization of the GDT, global description table, of the memory mapping. Then we're going to load the kernel from the disk drive into memory and jump to it. So the main job of bootmain.c is to load the kernel and then to jump to it. Once we are jumping into the kernel, we finished our job, the boot is finished. Okay, then another thing is you expect to find a copy of the kernel executable on the disk starting at the second sector of the drive. Meaning that we expect, first of all, we expected that the boot ASM was in the first sector. First sector was the bootloader from here, and the second sector will be the kernel executable in the disk. The kernel executable is an ELF format binary. An ELF is a format as for example exa file or a text file or any format or bin file. There are many formats of files. So one of them is ELF. ELF is a structure of file which has first of all headers, that those headers helping understand how the other file is composed of. And after the headers we have data, and after data we have instructions, And it is a way to write executable. So we have the kernel in a ELF format. With okay, and to get access to the ELF headers, bootmain loads the first 496 bytes, 4096 bytes of the ELF binary into this address. Okay, let's see how it is implemented. Okay, this is the code. Uh, we initialize this function wait disk, which is a while loop that wait for disk to be ready. And we have another function called readsect, which read a single sector with an offset into destination. So it wait for the disk to be ready, read the sector, and then wait for it another wait for the disk. And we have readseg function. Wait. So we have a readseg which use readseg which use readseg, which able to load and read multiple sections using each readseg function. So this is those function implementation, and then we have the boot main.c here, which what it does, it goes into this address. This is the address that we expect the kernel executable to be, and then we read it and we read all the sections to load the kernel. Okay, so this is generally it. You have a okay, so wait disk is waiting for the disk status to be ready. We have the function readsect that read a single sector given an offset, and we have function readseg that read continuous part of the kernel image using calls to readsect to read one sector at a time. So generally, the function boot main analyzes the section in the ELF headers, read them using readseg. ELF also contain destination address, and at the end dump into entry, which is a code that you're going to see right now, to start the kernel execution, and it will not return. Okay, what is kernel entry? So once we jump into kernel entry, you can see it here, we jump into entry. Then the main job of entry is to initialize the CPU. So we have two codes, entry.s, which is an assembly code, and entry other.s. So since in xv6 we have two CPUs, two cores, then this is for the default CPU, entry.s, and we use another assembly file to initialize the second CPU. At the end, after completing entry, we jump into main.c. So let's see it. I want to show you first main.c. So after entry that we're going to discuss right now, we're going to jump into main. Main is the final process in the boot, meaning that we initialized important things such as initialize interrupt, we initialize the page allocation and the kernel page table and process table and buffer cache file table disk processes and so on. And then we start the first user process, which the first user process is going to initialize the shell And once we are in this place, then we can start a simple execution with the operation system using the shell and our user commands. Okay, so this is about main.c. Uh, let's see entry.s. This is the implementation of entry.s, which is in also in this code in the 1000 in here. This is entry. So what it does, it when we enter into this boot, when we get into this entry, we are still with paging off. We don't have any paging, so we turn on paging. Let's say in here. So xv6 bootloader load the xv6 kernel as we saw from disk, and then start executing entry. The x86 paging hardware is still disabled when the kernel starts, and virtual addresses map direct to physical addresses. And the bootloader load the xv6 kernel into memory at physical address 100,000. So, first of all, the reason that we load this kernel into memory of this number and not 0, for example, is that we expect that any addresses until this is allocated by any I/O devices. So this is the reason that we load it into here. And another reason that we don't load the kernel into this high value is because we do not expect the memory to be such big. Okay, so in order to allow the rest of the kernel to run, the entry set up the page table. Now we have a mapping from virtual address into physical address, which is not one by one. We added this kernel base, meaning that every kernel processes will have this offset to ensure that kernel and the user processes are not aligned. Okay, so let's see it in the code. Okay, we do it later. Line so entry.s is jump into this entry point. We get here from the bootloader C file boot main.c. We turn on paging. We set up a kernel stack. We transfer control to main.c, and we start with I address. Okay, so how it is done, the mapping in entry.s, meaning how we enable the page table. So we're starting by one-to-one direct mapping from virtual address to physical address. You see it here from 0.4 megabyte to 0.4 megabytes. And then we have another mapping. We go into a mapping where we add this kernel base. Kernel base is this number. So we have enabled the page table mapping. Okay, so at the beginning in entry.s, the page table mapped virtual addresses one to one, for example, 400,000 to physical address 400,000, and then then entry is going to map virtual addresses using this offset, kernel based offset. So for example, this code will be mapped into 800,000. Never mind. yeah, 800,000 with this offset. It's here with this offset. Okay, then main.c is called from entry.s, initialize the kernel subsystem, then create the first process. The first process is in initcode.s. Initcode.s will use exec system call. Exec system call is enabling user processes to run. So init.c will execute a shell to accept user comments, and that's how the boot is loading, and that's it. Okay, so see you next week, and goodbye.